Assalamualaikum warahmatullahi wabarakatuh. Today I am Muhammad Luman Rakim Halimur Rashid bin Darwis, AE 2015. We are going to discuss about case study, three-phase fault analysis at compact power system. So for the introduction, in this case study, we are focusing on doing a comparison between a three-phase system with and without faults. So uh, for the conclusion, uh, we are exploring how this simultaneous fault in compact power system can be impact their reliability and what solution might be necessary to overcome such challenge. And we focus on how to get the value from voltage and current itself using MATLAB simulation. So the problem statement that we can see here is the voltage and current fluctuation. The second one is protective relaying coordination, and third, the modeling and simulation challenge, where we focus on how the first one we focus on how three phase fault lead to an abrupt changes and surge in current, affecting the performance and connected device and equipments towards the compact power system. The second one is protective relaying coordination, which the effectiveness of protective relaying system in isolating faulty section and preventing widespread damage is paramount. And the third one is the unique characteristic of compact power system necessitate accurate modeling and simulation studies to anticipate and mitigate the impact of three-phase faults. And in this case study, we are more focusing on using MATLAB Simulink to provide the actual result for this case study.
Assalamualaikum. My name is Muhammad Farhan bin Muhammad Yusof, CE210182, and I will continue the presentation by explaining the methodology of the project. First is the flowchart. In the pre-simulation stage, the Simulink model is prepared by defining key parameters like resistance, inductance, capacitance, voltage characteristics, frequencies, and also faulted phases. The circuit construction phases involve using Simulink's graphical interface to position an interconnect block representing the electrical components. Accuracy in representing the physical system topology is crucial. Moving to the simulation execution, the process begins by running the simulation to calculate the transient response under a specified fault condition involving the numerically solving governing differential equation. Post-simulation analysis includes voltage and current analysis, examining the interpreting waveforms at the critical points using tools like oscilloscope. An optional protection scheme evaluation assess its effectiveness in detecting and isolating faults. In the result and conclusion phases simulation, outcomes are interpreted. Critical fault types are identified, their impact severity assessed, and effectiveness of protection mechanisms also evaluated. The process concludes with documenting key findings and insight, potentially including graphs and tables, summarizing fault behavior and mitigating strategies. Now, let's continue with the block diagram of the project. In the initial stage, depicted in the figure, an unbalanced fault occurs in the power system due to the reasons such as load imbalance, defective parts, or line-to-line faults. The fault is characterized by unequal voltage or non-120-degree phase differences in the three phases L1, L2, and L3. Fault detection involves monitoring the monitor system for variations in current and voltage. The protective relay system is then activated upon fault detection. Determine the severity and types of faults. Emergency response follow the predefined threshold and decision logic to select the most appropriate response. The flow continue with drift command and clearing initiated when the protective relay system deems the fault severe enough. This command triggers fault circuit breaker to isolate the clear faulty section. Control and regulation functions ensure the rest of power system operates normally during a fault by adjusting the generator output, sharing loads, also taking other control action. After clearing the fault, the stability of the entire power system is analyzed, determining if it can return to the stable operating point. If not, additional actions may be required to restore stability. Finally, All the data and actions related to the fault are fed back to the power system model built simulated using MATLAB Simulink. This model represents the real power system behavior, facilitating ongoing monitoring, operational planning, and also performance analysis under different fault conditions.
For the simulation connection for the without three-phase fault, we have used generator as the source of a three-phase power system. Next, the three-phase breaker as a circuit breaker to protect the circuit, and it will interrupt the current flow if it defects a fault. Then, a three-phase series RLC load representing any load. After that, DMUX 1 and DMUX 2 is used for a digital multimeter to measure a voltage and current. Next, the measurement used can be monitored from scope to display waveform for each phase. Besides that, power GUI is used discrete because it is a tool for simulating and analyzing power system in the time. Finally, the relay is external source and act as electrically operated switch. The stop time set to 0.3 second to the waveform will run until 0.3 second and the step was adjusted to 0.1 second. After that, the step will activate the three-phase fault to trigger the fault at 0.1 second. For the simulation result for a voltage waveform, the figure shows the voltage waveform flows through the system in normal condition until 0.3 second because there is no such fault in the system for each phase. The voltage value for 11 kV is 1.456 times 10 to the power of 4 volt uniform phase for each phase. The voltage waveform across each phase is a balanced three-phase system behave in a sinusoidal manner resulting in a symmetrical pattern with uniform spacing. For the current waveform, the figure shows that the current waveform flows through the system in normal condition until 0.3 second because there is no such fault in the system for each phase. The current value for 11 kV also have same value which is 1.456 times 10 to the power of 4 ampere. Uniform phase for phase A, B, and C. In a balanced three-phase system, the current waveform likewise shows sinusoidal behavior under typical operating condition.
Okay, this is simulation result for three-phase fault. For the three-phase fault, we include the three-phase fault in the simulation. For the simulation analysis, the figures show that the voltage flow normally from 0 second to 0.1 second with the value is 1.456 times 10 power of 4 volt for the voltage. At 0.1, the step actuate and make the fault occur because of when the short circuit happen, a lot of current is produced and the voltage approach to zero rapidly. The voltage waveform across each phases of an imbalanced three-phase system diverges from the ideal sinusoidal pattern, which is symmetrical and evenly spaced. The figure show that the current was flowing normally and the current is about 1.456 times 10 power of 4 amp from 0 second until 0.1 second. Then fault occur at 0.1 second because of the step function actuate at the three-phase fault time and induce into the current. At the same time, huge amount of current fault occur around 6 times 10 power of 4 amp is more than the comparison value of the relay, which is 30 times 10 power of 3 amp. So the current have exceeding the relay activity. That is why the current reduced until 0 at 0.1 second.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan Menhot with metric number CA21016. So today I will explain about the conclusion. So in conclusion, the case study discussed about the three-phase fault analysis in compact power system. So the study includes the analysis of voltage and current waveform on both balanced and unbalanced circuit, in addition to fault detection system as well as an array of protective relay system that are utilized across all circumstances for providing a notification or initiation response to such issues. So it further mentions simulation tools like MATLAB Simulink for modeling and analyzing power system over time. Next is the comparative assessment of behavior between balanced and unbalanced fault in a three-phase power system. Unbalanced fault waveforms such as voltage fault, current fault is a comparison value at the relay which is 30 kilo amps, so the current have exceeding the relay activated. That is why the current reduced until it reach 0 amp at 0.3 second. So that's all for the conclusion part. So thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan Hot, with metric number C210186. I am from section 2. So for our title is three-phase fault analysis in compact power system. So today I will demonstrate our simulation part. So we are using MATLAB simulation for our project, our assignment, our task. And then the first one is here is the three-phase source is the generator. So for the generator, we are using YG configuration, and then face-to-face voltage VRMS 11 kV. Frequency here is the 50 Hz, and the base voltage VRMS face-to-face is same like at the top, 11 kV. And next, the important thing here is the three-phase breaker here is a circuit breaker which is it have 4 inputs and 3 outputs, and the circuit breaker will actuated by external mechanism. Here is the relay. So so I'm just controlling the switching time here by the external source, which is obviously our relay. So the breaker resistance here is 0.01, and the snubber resistance here, everything here is set. And then the next step is three-phase VI measurement. So this is to measure the excessive current passing through the system. So they have 3 input and also 3 output here, because they have same to same load, but we have VA-BC and also ABC that have to measure here at the scope here, voltage and also current. And then we go to the three-phase fault, which will be induced in the current before the load here, and then the step time here is this three-phase fault will occur when the step function here actuated in this mechanism. So basically the step time here is 0.1. Whenever the step time is 0.1, the pulse will be generating from the step time here into the three-phase fault, and fault will occur here. So next is the relay. So for the relay here is this is the relay circuit here is basically is theoretical, is not practical because of the SR flip-flop. So basically this here is we have to compare the input of the current is cross certain limit or passing the limit of the relays. So basically the limit of our relay here is 30 times time 10 power of 3, and then the output here is going out here and enters the breaker here. And then as fault occur, the relay compares the current is exceeding the safe limit. So breaker will operate here, and then we need to set the time here 0.3. So 0.3 is the stop time, and the fault will occur at 0.1 here. We have set the time. So next we have to run the simulation. Okay. So we have run the simulation. So for the current here, okay, for the current here, for the first 0.05 before the 0.1, the current will flow normally here, and then at the 0.1 it will actuate the step time will actuate the three-phase fault, and then fault will increasing until the relay haven't stop it until the current stays zeros. So this is the result for the current. And so for the voltage here is the same until it reaches 0. It will flow normally here, and then it increase and flow normally here is 0. And then for the balance fault, this before this I explained about I explained about the unbalanced fault, and then this is the balance fault. So for the current here, the current flow normally until the stop time here is 0.3. Here is for the current waveform, and then for the voltage waveform also the same. The voltage have the same angle, and also the value of the voltage is the same of each time here. And then that's all the unbalanced fault and balanced fault for the result. And that's all for our simulation. Thank you.